Welcome to today's video. Today we're going to talk about the last topic of the Special Relativity block, which is the consideration of accelerated frames. So we're going to learn a little bit more about non-inertial motion and what things look like from the point of view of an observer who is non-inertial. We will revisit some of the fundamental things that we talked about in the past, and we will readdress whether the speed of light is or not c for observers that are non-inertial. So we will see. Now, the first thing I want to talk with you about is a very simple calculation. I just don't want to put it out of my hat. I'm going to tell you a lot of things to compute yourselves, but I want to do this one because it's like neat to do very fast. Imagine that I have a frame Tx, an arbitrary frame, right? And I want to compute what is the derivative of the gamma factor, the Lorentz factor with respect to t. Well, that's easy. I do the derivative, and then I get this expression here that just applying chain rule. So that gives me gamma cubed minus 1/2 minus 2 and this factor here. Now, the arithmetic is very simple to follow. It's the derivative of a polynomial, right? And the chain rule. Now, when we get to this point, we identify here this thing, dx dt in the reference frame Tx is the velocity. And the second derivative is the acceleration. So we know now then that the 2 and the minus 2 and the minus 1/2 cancel. So we know that the derivative of gamma with respect to t is gamma cubed divided by c squared times velocity dot product with the acceleration. So this thing is d gamma dt in an arbitrary frame Tx. All right, so let's remember that is something that we're going to use. So let's store it maybe on that corner there, like that. And now we're going to define the notion of forward acceleration. Well, the forward acceleration is going to be a forward vector. Remember, if we have, this is the position forward vector, right? Then we define the forward velocity forward vector, which we call u mu or x dot mu, right? Which was defined, of course, as the derivative of the forward position with respect to proper time. I get a forward vector, I take the derivative with respect to something that is Lorentz invariant, so the result is a forward vector. Careful, note of warning. If I were to define this object, x mu dt, where t is not the proper time of the motion, if I were to do that, this thing is not generally a forward vector. This is not a forward vector, it's not a forward velocity. The forward velocity requires the proper time. This is a conceptual mistake that people make sometimes. This is not a forward vector. And in fact, this thing will not be Lorentz transform as a forward vector. Remember, to be a forward vector, you need to be a vector in the sense of transformations, right? The components of those things transform with lambda tilde, as we saw. Well, the components of this thing will not transform with lambda tilde. So interested, if I were to define something called, I don't know, u tilde or whatever, some mu like that, this thing has a superindex and yet doesn't transform with lambda tilde. So not everything that has indices is a tensor, right? There are some things that will have indices and don't transform properly because they're non-covariant, they're not tensors. So this object in particular, is not a forward vector. Okay? Good. That out of the question. We had our forward position, our forward velocity. How do I build another forward vector from the forward velocity? Well, I can now do the next step. Let me define the forward vector v mu, and I'm going to define that as the second derivative of x mu with respect to proper time. Again, this is a forward vector derivative with respect to something Lorentz invariant, proper time. Remember that the proper time is basically the same as the line element, ds. There's a c square of difference between d square and theta square, and perhaps a sign. But so this thing is certainly a forward vector. So we know that the components v mu will transform with lambda tilde under changes of coordinates. For example, changes of inertial reference frame. Very nice. So what is this forward vector? Well, let's see. Considering an arbitrary frame, an arbitrary coordinates tx, then we use that dt d tau is gamma, if you remember. And that the dx d tau, of course, is in chain rule, is gamma v. Then we found, if you remember from the previous videos, that the forward velocity forward vector is this form, is gamma multiplying cv. Now, to compute the forward acceleration, all that we need to do is take the derivatives of this forward vector with respect to proper time. Now, if we do so, we compute and we apply chain rule and we obtain the following. All right, so the first term it's easy. We use the formula that magically appear boxed here. And this formula, how can I use that? Well, I realize using chain rule that this factor is nothing but, this is gamma dt, but of course multiplied by dt d tau, right? That's the same as that, applying chain rule. Now, I recognize that dt d tau is a gamma factor itself, and d gamma dt is what we computed up there. So we can write the first demand as one extra gamma factor that gives gamma to the fourth divided by c squared. Now we get v dot a, right? One gamma from here and then three gammas from there, multiplying c v. All right, now the second term. The second term is a gamma, and now I have to play with, well, it's a zero for sure. And what is this? Well, same as before, the velocity. So this term right here is nothing but the derivative with respect to tau of derivative of x, the position, with respect to t, which is the velocity in that frame. All right, but we can use chain rule, and using chain rule again, this would be a d dt dx dt. Of course, I need to use the gamma factor here, right? This is chain rule again. This is exactly equal to that. This gives me a gamma factor, and this thing is the second derivative of x with respect to t in that frame tx, which is exactly the acceleration. Wonderful. So all that I need then to write here is that this is a gamma factor acceleration. All right, combining everything here, that gives me that the total for vector is going to be, well, let's recall that zeroth component. The zeroth component is, and I'll write the two things here, right? So this is going to be b super 0 b vector, all right? And let's write here what b super 0 is. Let's just combine nothing from this term, but from this term I get a gamma to the 4 divided by c, because one of the c is cancelled, times v dot a, that is v0. And now the vector b, the spatial part of the 4 acceleration, that's going to be, let's see, from here we get gamma to the 4 divided by c squared v dot a multiplying v from the first term plus a factor gamma squared acceleration. All right, so these are the components of the 4 acceleration. Okay, something that is a mistake that many beginners make is thinking that the spatial part of the 4 acceleration will be the acceleration. I don't know why people would think that. I think it's because it's called there's some myth that somehow is ingrained in people's minds. There's something called for something, means that the spatial part of it will be the try something, I guess. But certainly you can tell how this is already not true. The spatial part of the 4 velocity in a given frame is not the 4 velocity, is not the try velocity, is gamma velocity instead. Even more complicated, the relationship, the spatial part of the 4 acceleration is certainly not the acceleration. Now we can check, this is in an arbitrary frame, what about in the proper frame? All right, so in the proper frame, erasing this garbage. All right, in the moving particles proper frame, coordinates tau psi, if you want, we know that velocity is 0, I'm not moving in my own proper frame, and gamma is equal to 1. Well, if we go here, we see that v0 would be immediately 0, because v is 0, and the spatial part would indeed be, this term goes to 0 as well, because v is 0, this gamma goes to 1, and would be a, the acceleration of the particle. Now, in that frame, remember, a would be d psi d tau. So in the proper frame, you call it tau psi, right? The acceleration here would be d psi d tau. And of course, it's not 0. Even if I'm in the proper frame, I have 0 speed, but I may be experiencing acceleration. I may have an accelerometer that registers something. I may feel acceleration, right? And indeed I do. Now, this is super interesting because in the proper frame, this thing has the simplest possible form. In the simplest possible form of it, we can actually compute things easily, right? So one of the things that we can compute is the contraction of v mu with itself, kind of the norm of the 4 velocity vector. This is the same in all frames. This is a scalar. I get 2 4 vectors, and the contraction between 2 4 vectors is a scalar. So eta mu nu, b nu, right? And this thing is like here, the zeroth component is 0, so the zeroth component doesn't contribute. So what we get here is just a modulus square. So this is indeed the proper acceleration. So b mu, the square root of b mu is, we can call it just a if you want, is, well, actually I call it with modulus of a. This is the proper acceleration of the particle. In different frames, you would say that the system would have some acceleration a, but in your own frame, the acceleration is the contraction of b mu. Now, why is this useful? If somebody, and by somebody I mean me in an assignment, for example, tells you what is the transformation of accelerations, there are two ways of doing this. You can go and compute like crazy, like we did with velocities back in the day, and then just use chain rule and a lot of arithmetic, or you can compute covariantly, which is the way to do it. No, find some covariant object that contains the acceleration. What is that object? Well, the 4 acceleration contains the acceleration and is covariant. And now transform with a Lorentz transformation and find the expression of A. And that is the way to find how the acceleration transforms. Perhaps this is something that I'm going to tell you to do in an assignment, so I won't get much into that, but this is the best way to compute every time that you want. I want to transform the acceleration. What is the acceleration that I see as a function of the proper acceleration that that moving iPhone detects in their accelerometer? Well, I know that the acceleration that the iPhone will measure would be the square root of the contraction of the 4 acceleration with itself. And now what I do is I transform. If I know the trajectory of the iPhone, I can transform, I can compute the transformation from the moving frame of the particle at some time to my frame. And that will give me what is the acceleration of the iPhone as seen by me. All right, so before we continue, let me introduce a slight change of notation. I'm gonna, from now on, reserve the letter A small, not capitals, for the proper acceleration. That is, the acceleration of the particle as seen from the point of view of the particle itself. So the reading of the accelerometer that this particle carries, a particle that's moving, right, and carries an accelerometer, the accelerometer registers an acceleration, and I call that small a, proper acceleration. And I'm going to use now capital A, as opposed to small a, for the acceleration with respect to an arbitrary frame. It could be any frame, could be the proper frame, could be other frame, okay? It's an arbitrary frame, but it could also be a frame Tx corresponding to an inertial frame, an inertial observer. So I'm looking at the particle and I compute how much the velocity varies in time, and that's the acceleration capital A. So A, acceleration as seen from an arbitrary frame, think for example an inertial frame, and A, the proper acceleration as measured by the particle. All right? Good. Now, given that, I can write, of course, the component B0, the zeroth component of the 4th acceleration, and the spatial component of the 4th acceleration in terms of the arbitrary acceleration capital A that I have here, right? In the up to now, I wrote a small a for an arbitrary one, but I'm going to reserve the small a for proper acceleration, and I use capital A for the arbitrary frame acceleration. Now, we computed, of course, that the norm of the 4 acceleration, we computed right before, that this norm is easy to compute in the proper frame, and you get that is the square of the proper acceleration, right? So again, the norm of the 4 acceleration is the square of the proper acceleration. Wonderful. But we can also compute what this is for in an arbitrary frame, right? In an arbitrary frame, the 4 acceleration, remember, in the proper frame, the b0 was equal to 0, and b vector was equal to a, right? So very easily, b mu was just a square, which is what we did before. But in an arbitrary frame, well, b0 is certainly not 0, and b vector is certainly not a, right? So we can compute the value of the contraction b mu. We can compute that value in an arbitrary frame. So this is the result. This is what you get. Is it easy to see directly from here? Well, it's not difficult. It's just basic manipulation, but just for completeness, I felt gracious today. I did the calculation here. So let's check the calculation. I want the contraction of the 4 acceleration with itself. So this eta mu nu, b nu. So of course, this is minus b0 squared plus b vector squared. All right, so the step that I write here is precisely that. First term here is the square of b0 with a minus. And then I do the square of the vector one, which has 3 summands, right? First, the square of the first summand, right here. then the square of the second summand, right here, and then twice the product of the first times the second, which is right here. All right, so then we simplify with a small amount of manipulations here, we simplify this. We can take a common factor, gamma to the a divided by c squared v times a squared, all right, and that common factor is here in both. 1c squared, I pass it into the v here, and I get this factor, and this other one, then this minus 1 represents this one, and this v squared over c squared is this one. But nice enough, this thing is just minus gamma to the minus 2. So minus gamma to the minus 2 times gamma to the 8 give me minus gamma to the 6, right? So this term, these two terms, I can write as this term here. But nicely, this is the same term as here. I have two of them here, minus one of them here. I sum them, and I'm left with just one. So the norm of, if you want norm square, I'm going to use the word norm, of course, all the time. The contraction of the forward acceleration with itself yields this expression here, which is what I wrote here, taking a gamma to the 4 factor outside. Now, this is particularly useful because we computed the norm of the forward acceleration in two different ways. First, making use of the comoving frame. In the comoving frame is just the proper acceleration square, and another one in an arbitrary frame. And in this arbitrary frame that I have here, I got that the norm of the forward acceleration is given by this expression. Now, these two things are the same. This is the same quantity. Keep in mind that this is a scalar. So if I consider, for example, an inertial frame looking at the particle, and then the comoving frame of the particle, the norm of the forward velocity will be the same. I can equate these two things, and that allows me to relate the proper acceleration of the particle as measured by an accelerometer carried by the particle with the velocity and the velocity of the particle and the acceleration of the particle as seen from, let's say, an inertial reference frame that is looking at the particle go. Okay, this is how you relate the two. It's kind of nice. I find things that are Lorentz invariant, and then I can relate them into different frames. Through now equating these two things being equal, it will allow me to find the equation of motion for the accelerated particle and to define the proper coordinate frame of the particle, as we will see in a second. All right, so let's consider now. I have this thing is equal to this one. I wrote it here. I just put the c squared in here. And we're going to do a series of things to simplify the solution of the equation of motion with a loss of generality, though. Let me assume that I have a frame Tx, and in that frame, at time equals 0, it's co-moving with the accelerated particle. Okay, cool. And let's say that the acceleration only goes in the direction of x, which is just, for the case of constant acceleration, we don't lose generality. We are orienting the x-axis with the acceleration. If that's the case, both the acceleration, capital A, and the velocity v will have the same direction and will go in the direction of x. So we can simplify and remove the vectors from this equation. And now we can actually take a common factor a squared out. Let me do that. And now we have this factor here. But this factor is a very easy one, because if let's write gamma squared b squared over c squared. So that would be b squared over c squared divided by 1 minus b squared over c squared plus 1, which is very easy. You can see common denominator tells me b squared divided by c squared plus 1 minus b squared divided by c squared, all divided by 1 minus b squared over c squared. So this cancels that, and this is just gamma squared. All right, so all these parentheses is just gamma squared. Let me simplify them. Right, and now we know, therefore, that A is equal to gamma cube A. Wonderful. Well, that allowed me to solve the equation of motion for the accelerated observer in terms of the variables of the coordinates of the frame dx. How? Because I know what this is. This thing, let me write it like this. That means that A is equal to, let me substitute the gamma, well, I'll write it here, gamma cube dv dt. So I can write the equation, I can integrate this with respect to t. Let me just do it. I will have A dt equals dv over, and I substitute the gamma cube, would be here 1 minus v squared over c squared to the 3 over 2. All right, that equation, and that equation I can integrate. This is an integral that you should know, at least theoretically, you should remember. It's one of what we call immediate integrals. The result of this is this, which you may remember because this equation here when I saw for an example of a non-inertial trajectory, I picked this one. You can tell this comes from integrating this. So the integral will give you this, right? The assumption, of course, you need an initial condition. The assumption is that, as I said, at t equals 0, the velocity is 0. With that assumption, I integrate. With that initial condition, I integrate, and I obtain this equation. And I can integrate it again, because v, all that I did right in this bit is that v is certainly dx dt, right? So now I have dx dt, so I can integrate this, assuming that, let's say that the particle at time equals 0. So to do this, I assume that at t equals 0, we have, or maybe let's write like this, v of t equals 0 was 0, to integrate that. We can now integrate this one, assuming that x of t equals 0 is 0. So if we do that, we obtain this trajectory. So if you want, you can call this one x of t, if you want. All right? This trajectory is the trajectory of the accelerated particle. X a function of t. The trajectory is a function of the time of the frame that is observing it. Say it's an inertial frame that is observing it. And a is the constant proper acceleration. Here a is the proper acceleration. Wonderful. Now, let's dig a little bit more and let's try to use the relationship that we already have done when we solved. Remember when I gave you an example of finding the relationship between proper time and the lap frame time that we did in the previous video? Well, let's put it to use. Let's now use the relationship between proper time, tau, of the particle and the time t. How do we do that? Well, let me just refresh you, not to have to go to the other video quickly. Let's do it with this. The relationship, again, as we did in that video, the relation between the d tau dt is gamma minus 1. We substitute gamma minus 1, we get dx dt in here. That's the velocity, v squared. And we already know the expression of dx dt in here. We just plug it in and we take this expression. Awesome. So remember, this thing is the tau, d tau dt, right? So we can now integrate this to get tau as a function of t. So if we do that, we obtain this expression, which we can invert very easily and get that t as a function of tau is c over a hyperbolic sine of a tau divided by c. This we already obtained in the other video. Now we can get x of tau as well. We have x of t. So all that I need to do is substitute t by t of tau, and I will get x of tau. So if I do that using this expression, plug in this expression in here, and using hyperbolic relationships, I obtain this expression. All right? So this expression x of tau we obtain by plugging in t of tau in here. I'm playing a little bit with the hyperbolic trigonometry relationships. All right, wonderful. So we got the trajectory, if you want, of the accelerated particle in the frame tx, parameterized in terms of the proper time of the particle. Now, this allows me now to define a coordinate system that moves the relationship between the coordinate system that moves with the particle and the coordinate system tx. Let's call the coordinate system tx the lab coordinate system, an inertial frame, and the particle system is tau xi. And it's easy because we know that the trajectory of the particle would be the tau axis, right? In my proper frame, I'm moving in the time axis all the time. I'm moving in the direction of my force velocity has the direction of time, right? So I'm moving only in the direction of time. So that's the tau axis. And we can get the x-axis. How do we get the x-axis? Well, we get the x-axis by defining the place of simultaneity, right? At a constant tau, I can check what is my instantaneous velocity, and I have a Lorentz transformation that tells me how the axis tilts with respect to the lab frame. Remember what a Lorentz transformation does? It tilts the axis like that? Well, with a constant acceleration, it's tilting the axis increasingly fast. You see, it starts with velocity. They're the same axis at time 0, have the same velocity that's moving with the lab frame, so velocity is 0. As it accelerates, velocity increases and the axes start tilting. And at infinite time, the particle reaches very close to the speed of light and the axes are fully collapsed to the 45-degree line. The trajectory of the accelerated observer is a hyperbola. So unsurprisingly, the trajectories of things that have constant psi, constant position in the proper frame, would be also hyperbolas. We can even obtain them easily from dimensional analysis. So let me just write the transformation like I have a frame Tx,
which I call lap frame. And I have a frame tau psi that I call proper frame, which is the proper frame of the particle, as proper frame.
Alright? Then the transformation between them is going to be given by the following. This transformation. And this transformation is just saying, well, the lines of constant, the trajectories of constant proper position will be hyperbolas, and this is the translation that displaces the hyperbolas consistent with the acceleration that this particle has. And as you can tell, psi 0 is exactly the position of the particle that's moving, right? Psi equals 0 gives me exactly the trajectory of the particle. All right, this frame, this proper frame, is the frame in which, you know, the accelerated observer has rulers and watches. So this is the frame in which the accelerated observer, if you want, will be measuring. We call these coordinates the set of Rindler coordinates, like this Rindler, adapted to the trajectory of this particular particle. All right, so now that we have this, this transformation of coordinates, by the way, you could have already guessed more or less the transformation of coordinates without having to do the reasoning of the planes of simultaneity that we did by dimensional analysis. To get a little bit more insight, because it's a question I get often, a bit more insight on this coordinate transformation, just think of the following. Let's write a transformation in which I parameterize trajectories of constant position are going to be hyperbola. So a hyperbolic transformation. And of that hyperbolic transformation of coordinates, pick the one for which the trajectory of the particle is that of the tau axis. All right, there's only one possible transformation, and it's this one. So only knowing the parameterized trajectory, it's very easy to complete what's missing to find the change of coordinates. Because this is, you write the generic form of a hyperbolic change of coordinates. So t, it's equal to, let's say, constant d, xi minus x0, something like that, and then sinh of sigma tau. And I write here x, it's equal to some constant d prime, and then xi minus psi 0 cosh of sigma tau. That's a generic hyperbolic change of coordinates that will make the axis hyperbolas. And you adapt it so that it reproduces that the trajectory of the psi equals 0 axis, right? The time axis is given by this, and this is the only possible solution. That's how you obtain it. All right, wonderful. So we have these coordinates. Now the question is, how does an observer that has proper coordinates tau psi see space-time, sees the world, sees things happening? And for that, we're gonna do two things. We're gonna first do a calculation, then we're gonna do a little game, and then we're gonna analyze the speed of light as seen by the proper frame of this constantly accelerated observer. Before we do that, if you ever heard, oh no, special relativity cannot handle acceleration, well, there you go. We are handling acceleration in special relativity. Of course you can. What special relativity cannot handle is just gravity, but accelerated motion in the absence of gravity, no problem. How is that? Okay, let's get to it. All right, so I use my amazing drawing skills, apologies in advance, to illustrate what's going on here. You know, psi equals 0 is the trajectory of the accelerated observer. Say at time 0, the position is x0, and there's no velocity. The velocity is 0, right? In the sense that the velocity is only going, the forward velocity goes in the direction of t. So it's moving with the frame, 0 velocity here. But it's accelerating, and eventually it accelerates to the 45-degree line that represents going at the speed of light. So it accelerates towards the speed of light, of course, at infinite times. The trajectory is a hyperbola. Now, the axis, the spatial axis, this is psi equals 0. This is psi larger than 0. I mean, let's say psi equals 2 or something like that, psi equals 3. So the lines of constant psi, constant position, are hyperbolas. Of less exaggerated, less curved hyperbolas as we go to the right. Now, the hyperbola psi equals to minus c squared over a is this straight line. So the hyperbolas here are more exaggerated as we get negative, right, on the psi, like more exaggerated, and they get piled up, and when psi is equal to minus c squared over a, this is the general hyperbola that you get, the straight lines. Because you cannot see below past that. So the psi is not defined. The coordinates of that person are not defined for psi below minus c squared over a. There is a horizon. There is a horizon that this person's action, that the accelerator, there are parts, by that I mean there are parts of space-time that the accelerated observers cannot have access to. Their spatial coordinates cannot run past this value. So for that accelerating person, there's a horizon. And it makes sense, because somebody here can never send signals to the person in here because light propagates at the speed of light, therefore follow 45-degree lines. So light emitted from the negative part, so below minus c squared over 8 here, will never reach the trajectory of the accelerated observer. So indeed, this accelerated observer is limited to this wedge of space-time. Cannot access the whole of space-time because it's constantly accelerating forever. This has implications, and for those of you interested in this stuff, there are when you have a quantum field living in space-time, in this flat space-time, we talk about what would the accelerated observer would see when looking at the field. That's something called the Unruh effect. I'm not going to deal with it in this course, of course, because that requires quantum, and this course is not quantum. But if you're interested, I have a PSI course in which I actually talk about all this. It's called Relativistic Quantum Information. Anyway, advertisements finished. Let's keep going. So this person, the planes of simultaneity are going to be changing. So, the axis would be, if you want, tilting, right? So the place of constant tau would be like this one would be, of course, for tau equals 0 is the same as this one, right? It's the same as t equals 0 because they're moving with the same velocity, the last frame and the accelerated particle. And as the particle keeps accelerating, of course, the time axis curves, right? And that's what is expressed by the hyperbolas, but also the place of simultaneity. So the points that have the same value of the coordinate tau, it will start tilting like this, going up all the way in the end to the 45-degree line. That's what happens. Now let's take a closer look at what space-time looks like for that person. Now I know that the Minkowski metric, the metric for flat space-time that we saw, the line element, rather, I can write as this, minus c squared dt squared, in the left frame coordinates dx, which is inertial, an inertial frame, dx squared. Right. And now I can compute dt and I can compute dx, and if I compute dt and dx, I can substitute in here and write ds squared as a function of d tau and d psi. I can do that. Well, if I do it, what I obtain is the following. So we have the ds in terms of the coordinates tau psi has this form that I wrote here. How do we know that? Well, all that you need to do is compute dt and dx as a function of d psi and d tau and substitute in here. And you may be wondering, hold on, with so many hyperbolic functions and differentials, more and more hyperbolic functions will show up and so on. Should I believe you that this is true what you would get? Well, you don't have to, because I'm going to show you a board capture that does all the operations. You can pause it if you want that, so you don't have to believe me. You can actually check my math right now. Okay, I hope that you were convinced now that you see that indeed this is the same thing. So look at this. The line element, at least on this wedge of spacetime, the line element of the Minkowski metric, the flat spacetime metric, it's the thing that we saw in the previous videos, can be written in terms of the coordinates of the accelerated observer, tau psi, in this shape. That's kind of cool. By the way, you see here how when psi is equal to minus c squared over a, we have a problem. This thing cancels and we lost the line element. This is what we call a coordinate singularity. We will not talk more about that until we see differential geometry and general relativity. We will talk more about coordinate singularities there. Oh my god, see, we're going to talk about that, and we're going to talk about black holes and real singularities versus coordinate singularities and things like that. But this is a manifestation of the fact that indeed there is a horizon in here. The person that's accelerated cannot receive any signal from outside of that wedge, right? The coordinate cannot just get through the value minus c squared over a. All right, cool. So this is space-time as seen from an inertial observer perspective. Actually, from all inertial observer perspectives, remember that we saw that this was invariant and the Lorentz transformations. And this is the line element as seen from a constantly accelerated observer. Why don't we compute the speed of light? All right, let's remember what happens with light. So this is an equal sign, huh? So it's the line element of the flat space-time that we have here. Nothing is curved or anything like that. All right, let's see. Speed of light. Why don't we compute it first for the inertial case? But that's easy. What is the characteristic of the speed of light? Well, when we talk about light, remember the first videos that we saw, in a time t, the light covers, in a time dt, say, light covers an amount of space c dt. So for light, ds squared is 0. Delta, remember, for light, delta squared was 0. And in particular, you can say that the differential, so that ds squared along the trajectory of light is 0, right? When you advance a little bit of position at the speed of light, this factor cancels this factor. So indeed, you characterize the trajectory of light by ds squared being 0. All right, so I can write 0 for light. Let me just write it here. For light. So I write that 0 is equal to minus c squared dt squared plus dx squared. Oh, but that means that dx dt squared, it's equal, so if you want to reparameterize everything in terms of t, or if you want to really alarm pure mathematicians, which I recommend you don't do, but if you want, you would say, all right, yeah, kind of divided by z squared. No, this is dirty math. This is what we call dirty math all the time. Math that never should do, but works. You better know why it's wrong and how to do it right if you want to use it. Anyway, d squared dt squared equals c squared. Oh, nice. So of course, dx dt equals c. The speed of light for light that ds is equal to 0, we obtain that the velocity, the amount of space by the amount of time it takes to cover it, is c. Wonderful. Is that the case? And by the way, we know that this is the case for all inertial frames because the line element is the same in all inertial frames, as we saw in the previous video. It's a Lorentz invariant thing. What happens when we have an accelerated trajectory now, an accelerated observer? Well, for light, let's see, I don't want to anticipate anything. For light, we get 0 equals minus 1 plus a psi c squared c squared d tau squared plus d psi squared. Oh, but that means that d psi d tau squared is equal to, and I write here, 1 plus a psi c squared c squared. If we take square roots, d psi d tau, it's equal to 1 plus a psi c squared c. So the speed of light as measured in the accelerated frame is not c, it's c times a factor. Now, before we get scandalized, let's observe something. If you're measuring the speed of light exactly when a ray of light intercepts you, very close to you, around psi equals 0, you can tell that indeed the speed of light is c, right? If this is 0, the speed of light is c. So if I measure the speed of light very close to where I am, then the speed of light is c. But if I'm measuring the speed of light far away from me, say that I prearrange an experiment that tells me the amount of distance covered and the amount of time covered according to my clock. So I set up some experiment that tells me, oh, this is the delta psi that you have and the delta tau that you have of light going. That's how I will see light moving if I measure it with the use of mirrors or other tools far away from where I am in my frame. So this is tricky, huh? This is again a tricky point. But without getting into more, the speed of light as measured at positions that are a little bit far away from me is different from c. It could be less than c, and in fact, very close to 0. And it makes sense, right? This is a horizon. So light is going at 0 speed at the apparent horizon that I have here, the acceleration horizon that I have here. So close to the horizon, the velocity of the speed of light is 0. And far away from me, the speed of light is arbitrarily high. It could be anything, depending on my acceleration and psi. Again, if I were to measure light literally very close to me, like locally, if I'm only able to do local measurements, certainly I would find that when psi is 0, which is my trajectory, the trajectory of the accelerated observer, then the speed of light is c. But if I measure the speed of light going around, I measure for a while, and I set up an experiment with bars that can move with me, and I see light going through the first one, they send me a signal, and then I know when light went through. And I have another one and sends me a signal and tells me when light went through, and I'm measuring with my clock the difference in time, pre-synchronize. I need to synchronize with the clocks carried by these two persons, but I did it already. I pre-arranged the experiment. Then I would measure a speed of light that is faster or slower than c. Not only that, we can integrate this equation to find what's the trajectory of rays of light like. Well, That is the trajectory of light. So as you can tell, it's not a straight line. Light in vacuum will not propagate in straight lines. It's accelerating. The speed changes. It doesn't go in straight lines in space-time. I'm talking in space-time. So it would not be 45-degree lines anymore. It would be something else. It's curving like this with this curvature. The trajectory of light in space-time. Important then, messages. If I am a non-inertial frame, the speed of light may not be the same in the whole of space-time when I measure it. However, if I measure it very close to me, then the speed of light would be c. We can talk, and I hope we talk a little bit about what kind of experiments can actually give you the speed of light far away from you when you're accelerating. You can have an array of people that are moving with you. They go with different accelerations, but you see them in the same constant positions as you go. And you can communicate with them and coordinate your clocks and have measures. That's what we do. We never do there is no such thing as a local measure of speed, because to measure speed, you need to measure position at 2 different times. So things need to move from one time to another. When you have a speed gun, you're doing measures of speed of something that is far away from you. So this is not an illusion, even though you will hear that, oh no, but there are caveats. Well, it's not really an illusion in that sense. So the same way you measure the speed of a car with a speed gun, for example, you may argue, but a speed gun uses light. Yeah, sure. But if you prearrange a way of measuring an increase of distance, delta psi, divided by an increase of time, delta tau, in my frame, as measured by my clock, and as measured by my clock, as by my measuring tape, then certainly the speed of light is not c. It's some factor that could be range all the way from 0 to infinity, depending on how far I'm measuring the speed of light and how strongly I accelerate. So there you go. The speed of light is not c for all observers, only for inertial ones. And you can maybe say, well, locally, if you measure really locally, then it's c. Yeah, sure, but there's no way to locally measure the speed of light. And I really hope that makes you kind of outraged, and we can discuss in the live sessions. I look forward to it. All right, there's one more thing to show you, which is related to accelerated trajectories, and it's in fact a problem that you will have as an assignment to solve. But let me illustrate it with some slides. All right, now that we've learned about accelerated frames and what the world looks like from the point of view of a constantly accelerated frame, let me give you a little riddle that will be an assignment that you'll have to solve. Oops. Right. Oops. No. Okay, so I have here a scenario. This is the world in which theoretical physicists live. Here, the world, you have the usual stuff. You have spherical cows, massless spherical cows, and things like that. And in this world, these are 2 rockets. And these 2 rockets have identical engines, and they're tied by a rope. There's a rope tying them. And then at some point, they lift off with the same acceleration. Wow, lift off, and they leave. Now, the question we can ask is, does the rope tying them break or not? They have identical engines, and they're ideal engines. They go with the same proper acceleration, both of them. And the question is, does the rope break or not? This is what is called the bell-rocket paradox. Like now in relativity, with something is called a paradox, it means that if you're naive about it, you're going to think there's something contradictory. If you do it right, of course, you're going to get the right answer. Let's see. We will also ask why. Although why is certainly a dangerous question when we talk about physics. I would argue that physics is really good at answering hows, but whys are difficult questions. If you want to know why, search Feynman about magnets. It's a great video, and it's the question about why answering whys is difficult is addressed in there. All right. So let's analyze it. So we have 2 rockets that undergo constant acceleration, right? The x-axis here is the height of the rocket. So the rockets go on the x-axis as time goes, and they accelerate following hyperbolic trajectories, parallel. They have the same acceleration, and they eventually will reach the speed of light, 45 degrees, right? So from the point of view of the lab on Earth, from you, you're looking at the rockets go. You say, okay, at time t0, the 2 rockets are here. Then at some time, I have the simultaneity plane here, and then at t1, the same distance between them. And at time t2, yeah, the same distance between it. Okay. Then you may conclude there that the rope doesn't break because they are always at the same distance, which makes sense. They're accelerating with the same acceleration. You see the same acceleration in both of them. So certainly, there's nothing that would make this rope break, you would say. Okay. Now, from the point of view of the accelerated observers. So let's say we're in one of the rockets, and then we write the planes of simultaneity. So the plane of simultaneity from the rocket's perspective at time 0 is the same, right? Obviously, because they're not moving at time 0. Then at time 1, t1, here's the plane of simultaneity. And at time t2, here's the plane of simultaneity. Oh, well, that's a problem. This guy may be seeing the other rocket accelerate faster, and it's like, dude, slow down. What are you doing? You're accelerating much faster than me. And the other dude said, no, you are accelerating much faster than me. You're going to break that rope. Oh, okay. Oh, you're going to break that rope. So the question here is whether the rope breaks or not. From the point of view of the accelerated observer, it seems that it would break. From the point of view of the observer, the inertial observer, seems that it may not break. So what is the right answer? I will not reveal yet. Make your bets about it. It's funny because usually physics audiences get this one wrong. Like people who don't know physics, you get 50-50. But if people know some physics, if they know relativity, they tend to give an answer majoritarily, and it's the wrong answer. So this is very interesting thing that I've always observed when I ask that. Unfortunately, in online lectures, I don't get the chance to ask you. Well, now let's see. Let's see. Again, remember from the inertial point of view, the two rockets are at the same distance, so the rope shouldn't break. And from the point of view of the accelerated observer, the rockets are drifting apart, and therefore the rope will break. Well, the answer is that the rope breaks all right, and then you need to reconcile what's going on. Well, from the point of view of the accelerated observer, right, a little bit about the difference between the physics, what really happens. So the rope breaks is a fact. It's not, cannot depend on the observer, because you can ask later, oh, can I use the rope you just used? And then the answer cannot be, well, it depends. If you ask me, no. If you ask this person, yes. No. The rope either breaks or not. And it does break. And from the point of view of the accelerated observer, is well, because B is just faster than us. They're accelerating faster. If you compute the acceleration of that rocket, as seen by you, is larger than your proper acceleration, and also larger than the proper acceleration of the rocket, and therefore the rope would break. How do you explain this from the point of view of the inertial observer? Well, I'm going to write something here that is not completely accurate, but gives the idea. Because both rockets, keep in mind, are going faster and faster. So the rope is an extended object. So what happens to the length of the rope as seen by the inertial observer? It would be Lorentz contracted. And of course, the breaking point of the rope is like, well, the rockets are extending the rope longer than the length of the rope, and then it would break. So it's not that the Lorentz contraction breaks anything. That's not a force, doesn't break anything. But instead, the rockets are inducing tensions. For the two rockets to be at the same distance from the inertial point of view, that needs to induce forces in the rope that would break it. It's interesting, above all, because that means that an extended object cannot be accelerated, all of it with the same proper acceleration. So if you have a long ship, if you want to keep it one whole as it accelerates, you cannot just accelerate every point of the rocket with the same acceleration. That would break the rocket. You need to do something, maybe have different accelerations depending on what part of the rocket accelerates. Don't worry, you are going to see this, you're going to solve this as an assignment. So this is what I wanted to tell you at the end of this video. Please think about this and be prepared to actually do the math, because there's going to be the math to do with what we learn in the course in an assignment to talk about this bell rocket paradox. As you can tell, there is no paradox. The rope does break. It just certainly looks from the inertial point of view that it shouldn't, because the rockets are the same distance. That is true. The rockets are always at the same distance, but that distance is longer than the length of the rope. That is actually different as they accelerate. You were to literally measure the length of the ropes and in laser pulses and put in mirrors, that rope has a length gamma L, where L is the length at time 0 if you want, and the rockets are definitely pulling out the rope and breaking it. Again, look forward to you doing the math. Well, this is all for this video. Make sure that you are prepared now to learn a little bit more differential geometry, because that's what the next video is going to be about. Until then, just take care.